All right, so let's go ahead and take, so all of these questions are really examples of, okay, all right, no worries. Are examples of applying the first part of the fundamental theorem of calculus. So you might notice in the way I've written these problems, I have not left myself a lot of room to write anything because I don't need it. The derivative of the integral from 2 to x of a function is the same function. End of story. Same deal down here. If my function is the integral from -1 to x of t to the 4th over t to the 7 plus 8 dt, then the derivative of that's going to be x to the 4th over x to the 7th plus 8. That's it. Because what we're really seeing here is that the derivative of the antiderivative is the same function you start with. We pretended like we did the antiderivative, we didn't actually do it. Then we took the derivative of the thing we're pretending that we found the antiderivative of, and then we got back to where we started because we did two things that undo each other. This third one here is a little bit more challenging because the upper limit is not just x, it's x cubed. And actually, someone was just asking about this earlier. One way I would encourage you to think about this process here is I plugged in x, I got sine of x cubed, and at the very end, I multiplied by the derivative of x, which is 1. Same deal here. I plugged in x, I got x to the 4th over x to the 7 plus 8, and at the very end, I multiplied by the derivative of x, which is 1, which I wouldn't normally write down. So that then when I do it for something that's not just x, it becomes very natural. And I say, oh, I'm going to plug in x cubed, I'm going to get cosine of x cubed, and then I'm going to multiply by the derivative of x cubed, which is 3x squared. And that is the more complicated version of this first part of the fundamental theorem of calculus. I will point out for this last one. So I will point out a couple things actually. This first one here probably not antidifferentiable. Like I have no idea what the antiderivative of sine of t cubed is. It probably doesn't exist. Same deal down here. This one, nope. I'm pretty sure this one also is not antidifferentiable. There are some functions that you just cannot find the antiderivative of. That's okay. We're not being asked to. But here we could. So I'm going to, bless you, do this one the long way for a second. Say, instead of actually doing the derivative, let's just find the antiderivative first. So the antiderivative of 3, from 3 to x cubed of cosine of t dt is equal to, well, the antiderivative of cosine is sine of t, evaluated from 3 to x cubed. We plug in the top one first, we get sine of x cubed minus sine of 3. And then if I want to take the derivative of that, the derivative of sine of x cubed minus sine of 3, well, the derivative of sine of some stuff is going to be cosine of the stuff times the derivative of the stuff. If you really wanted to, you could say the derivative of sine of 3 is cosine of 3 times the derivative of 3, but the derivative of 3 is 0. But the better way to think about that is just that sine of 3 itself is a constant, and the derivative of a constant is 0. And look, we get the same exact answer doing it this long way. But the whole point, well, not the whole point, but one of the points of the fundamental theorem of calculus is that we don't have to do this. We can just say, oh yeah, the derivative of the integral of the function is just the same function, and then we plug in whatever variable we have, and if it's more complicated, then we multiply by the derivative of that thing. Questions about this? Right, exactly. So on a test, when someone asks you, oh, that's, yeah, I got a good question coming up. When someone asks you something like, find the derivative of the integral from, I'm going to change it up a little bit, from the natural log of x to 2 of, sure, I don't really care what this is, e to the t over 1 plus t squared dt, we do not need to find that antiderivative because they're saying find the derivative of all that. And so we're going to get, well, e to, oh, I forgot something. I didn't forget, I just plugged it. Since the natural log of x, or the function of x, is in the bottom limit, we need to start off with a negative e to the natural log of x over 1 plus the natural log of x squared. Times what? The derivative of natural log of x, which is 1 over x. Just because I want to point something out here, I will point out that e to the natural log of x is itself x. So someone could ask you to simplify this reasonably and get negative x over 1 plus the natural log of x squared times x. And then technically you can cancel those x's and get negative 1 over 1 plus natural log of x squared. I don't think that's that important. If it were me, I would leave it like this. But you could simplify. Something else I want to say here. There really was. What was it, James? There was something else that was like, yeah, you should say that. Oh, I know what it was. Make sure that when you write natural log of x quantity squared, that you write this and not this. Because if you write it like that without any parentheses, the default assumption is that the natural log of x squared means the natural log of parentheses x squared, which then you can bring down the 2 in front, whereas you cannot bring down the 2 in front here. And then I'll also point out that for some terrible reason, I guess technically you could also write this as the natural log squared of x. I, as you can tell by the tone of my voice, really, really am not a fan of this way of writing it, but I guess it's technically correct. So you could write it like that, but if you love all things good, don't. I'm not a fan, but it is technically fine. So if you wanted to write it that way, you really could. It's kind of like how we write, it's kind of like how sine of x squared, we often do abbreviate as sine squared of x, and I happen to be totally fine with that, so I guess I should be fine with that, but I'm not. Whatever. The other thing I was getting to, yeah, where'd you go? I had a really cool problem all lined up. Where'd you go? Sorry, it's hiding from me. And I really want to find it because it was good. It was like, yeah. Sorry, one sec. We've got like a million problems here. Got 9. No, I'm just kidding. Oh, I know where it is. Sorry, one sec. One sec. I thought I knew where it was. That's what happens when you try to have all the problems ready and you don't have any ready. Sorry. Also, it's easy. Okay. So what I wanted to ask was the following. I want to find the limit as x approaches 2 of the integral from 2 to x of e to the t dt divided by the integral from x squared to 4 of t cubed. Which seems pretty terrible. What happens if we plug in 2? If I plug in 2, the integral from 2 to 2 is what? 0. And if I plug in 2 on the bottom, the integral from 2 squared to 4 is, which means we can do what for this 0 over 0 indeterminate limit? You can use L'Hopital's rule. So if you see something like this, where you've got limits of integration, where if you were to plug in what x was approaching, you would get 0 over 0. The idea here is to, use L'Hopital. So I'm going to rewrite this as the limit as x approaches 2 of the derivative of the top. The derivative of the top is e to the x over the derivative of the bottom, which I'm going to plug in. Well, first of all, the derivative of the bottom, I need a negative, right? Because the x squared is in the bottom part here. So it's going to be a negative. I'm going to plug in x squared. I'm going to get x squared cubed times the derivative of x squared, which is 2x. And then we can go along and actually plug in 2 and get something weird like e squared divided by negative 4 cubed times 4, which, yeah, sure, we could simplify that. It's negative e squared over 4 to the 4th. But this is a popular type of question, I feel like, in 21B, where people are like, oh, we're going to make them use the fundamental theorem of calculus and L'Hopital's rule at the same time by giving them something like this. Kind of cool. All right, but that's not what the meat of today's class is going to be about. So I think we should probably start talking about U substitution. Because if you haven't gotten there yet, you're certainly about to. So, substitution method. Substitute. I can spell substitution, yes. The substitution method. So we'll start off with an example. We're going to evaluate this integral, the integral of 5x to the 4th times 1 times x to the 5th plus 1 dx. And we're going to do this 2 ways. First, we're just going to multiply it out because we can. And I would say that's good advice in general. If you can multiply something easily and just end up getting powers of x with coefficients, like this is going to be 5x to the 9th plus 5x to the 4th. Those are both things we can just use the anti-power for. And we're going to get 5x to the 10th divided by 10 plus 5x to the 4th divided by 5 plus a constant. And I would probably simplify this and get x to the 10th over 2 plus x to the 4th. Let's see. But we can think of doing this a different way. So what we're going to do now is for this integral, 5x to the 4th times x to the 5th plus 1. The idea here is that, oh, question, sorry. It should be, yeah, thank you. I missed that. Good call. Yeah, yes, exactly. So when we're trying to think about doing a substitution, we're looking for, I'm going to say it this way, we're looking for the inside function of a chain. We're looking for the thing that if you took its derivative, it would also be there. So when I'm making my choice for U, I would like to pick something that when I take the derivative of it, the thing I get will also be in my integrand. So here, the seemingly good choice, not seemingly, the actually good choice, the right choice is letting U equal x to the 5th plus 1. And the reason is because the derivative of U, du dx, is, well, the derivative of x to the 5th is 5x to the 4th. And I have a 5x to the 4th in my integrand. So I'm happy about my choice. So then we're going to translate this integral from the variable x to the variable u. And I'm going to say this many times. The most important piece of this transition, of this translation, of this transformation is that we make sure that dx turns into du. And I will point out, dx isn't just equal to du. We have to use this derivative. I'm going to rewrite it in the usual way by taking both sides and multiplying by dx and getting du equal to 5x to the 4th dx and say, okay, well, I'm able to replace this expression, 5x to the 4th dx, with just du because they're literally equal to each other. I personally like to rewrite this so that the things that are next to each other are next to each other. It's not necessary. You can totally get away without doing this. I'm going to rewrite this as the integral of x to the 5th plus 1 times 5x to the 4th dx. So then I can say to myself, oh, 5x to the 4th dx is just going to be equal to du. And then after I've made sure that whatever I need to have with dx transforms into du, then I deal with the rest. But I really can't emphasize enough. It is vital that you make sure that dx transforms into du. And really, I should say, you make sure that whatever you need to soak up along with dx transforms into du, right? Because it's not just dx turning into du, it's 5x to the 4th times dx turning into du. And then we can deal with the rest. And the rest is going to be this x to the 5th plus 1 is just equal to u. So now our integral gets much, much simpler. We're going to rewrite this as equal to the integral of u times du. Or I'll point out u to the first times du. And the antiderivative of my variable to the first power is my variable to the second power divided by 2 plus c. You can't stop there. If you're finding an indefinite integral, also known as an antiderivative, you're finding a function, and the function you end with has to have the same variable as the function you start with. So since we started with an antiderivative of a function of x, we need to end with a function of x. So I have to replace u with what I said it was equal to, which is x to the 5th plus 1. So I'm going to rewrite this as x to the 5th plus 1 squared divided by 2 plus c. A couple of things. If you took the derivative of this, you should get back to there. But what I really want to point out is when you take the derivative of this, you get 2 times x to the 5th plus 1 to the first, and then you multiply by the derivative of the inside, which is 5x to the 4th. So when we're trying to identify u, we're trying to identify kind of the inside part of the thing that we are going to eventually would have to take the derivative of. Are these answers the same? Should they be the same? Yeah, they probably should, right? If you're finding the antiderivative function, it technically shouldn't matter which way you do it. You should get the same answer any way you do it. Well, almost. Let's see what I mean. If we multiply this out, yeah, I can probably fit this in here. I don't really want it. So if I multiply out x to the 5th plus 1 squared, you're going to get x to the 5th squared, which is x to the 10th, plus 2 times x to the 5th times 1, plus 1 squared, divided by 2, plus c. And if I break this up into the 3 fractions, I get x to the 10th divided by 2. I get 2x to the 5th divided by 2, which is just x to the 5th. And I get 1/2 plus c. So now let me ask again. Are these answers exactly the same? No, they're not. Are they the same enough? Yes, they are. As long as your antiderivatives differ by at most a constant, we're good to go. And technically, if you really want to be kind of, I don't know, nitpicky about it, you could say, well, technically, I'm going to call this constant C1 and this constant C2. And then you can just say that C1 is equal to C2 plus 1/2, and then they're actually the same. But the better answer is that if you're doing an antiderivative or finding an antiderivative or an integral, and you do it a different way than someone else, because there are some integrals we'll see later on where you could like either do a u sub, or you could either like do polynomial division, or maybe integration by, or sorry, partial fractions, which I know are things we haven't talked about yet. You might get a slightly different answer than someone else because you might have done it a different way that ends up grabbing you an extra little constant bit that the other person didn't get. And that's okay. So your answers can be different up to a constant. Questions about this before we do some more examples? Yeah. Oh, well, so let me ask you a question. Sorry, not to throw it back at you, but if I was going to find, say, the antiderivative of x to the 3rd, what would I get? Say it one more time. Not the derivative, the derivative of 3x squared. The antiderivative is wait, x to the what? No, x to the divided by? Right. Because whenever we do the anti-power rule, we get a new power and then we divide by the new power. And it doesn't matter if it's x or if it's u to the 1st. The antiderivative of u to the 1st is u to the 1 plus 1 divided by that new power. That's where we're getting the division by. So this one, though, we wouldn't have actually needed to do a u sub here. So let's look at a problem where we would actually probably need to do a u substitution, like the following. Let's say we want to find the integral of x cubed times x to the 4th plus 5 to the 19th power. Technically, you could multiply this out. Nobody should. If you multiply that out, you'd have like 20 terms. I don't want to do that. You don't want to do that. It's not easy to do. And it's not the point of the problem. So we're going to make a choice for you. And there are two criteria that I'm looking to satisfy when I make a choice for you. Now I'm going to say, we always would like for both of these to be true. They're not always both going to be true. Later on, we're going to do some substitutions where one of these things, or maybe even both of these things, aren't true and it still works out. But from the get-go, we would love for it to be true that one, we really, really want that the derivative of whatever our choice of u is also there. So we want that for our choice of u, for the derivative du dx to also be present in our integral. That's what we would love to happen. The other part, the other criteria is actually just how you might identify what a good choice for you would be. So typically, a good choice for you, or a way to identify where you might find a good choice, is look for things, functions, that are quote unquote stuck. Meaning maybe they're inside a square root, or the argument of a cosine function, or they're the exponent in e to the stuff, or they're being raised to a really big power, or they're in the denominator. Basically, if they're somewhere where you can't really expand it out or multiply by some other stuff, I would call that being stuck. And that's usually a good candidate for what you should be. Not all the time. And I should say, really, in this class, nothing is always true, right? I'm going to say things that are true a lot of the time, but there's almost always an exception to the rule. But it's usually a good place to start. So here, I'm going to let u equal x to the fourth plus 5. All right, my 5 looks terrible there. And I'm happy about this choice because the derivative of that, du dx, is 4x cubed. And I'm going to say that I'm happy because I have the derivative of my u in my integral. Is it exactly perfect? No. But I don't care about the 4 there. I can adjust for a constant multiple every time. So when I ask, is the derivative of my function there? I'm just saying, oh, my function is x to the 4th, and its derivative is, I don't care what times x to the 3rd, because I have an x to the 3rd. So that's good enough. Great. So then I'm going to rewrite this. People usually skip this step, and they just start off by writing that du is equal to 4x cubed times dx. And there's like 3 schools of thought on how you do this. My preference, and I think the best way, that's why I prefer it, is to make it so that the thing you have over here looks like what you have in your integral. So I have 4 times x cubed times dx. I don't have a 4 here, so I'm going to divide both sides by 4. So that I have 1/4 times du equal to x cubed times dx. And I have x cubed times dx in my integral. So I'm going to rewrite this. Again, I'm going to do it the way I like, which I'm going to write it as x to the 4th plus 5 to the 19th power times x cubed dx. And then we're going to start replacing things. Always the dx transformation first. So this x cubed times dx is going to get replaced by 1/4 times du. And then the rest of this x to the 4th plus 5 is just u. So my integral is going to become the integral of u to the 19th power times 1/4 times du. And typically, I made a terrible thing. Sorry, I try not to use 4s and u's in the same time because my 4s and my u's start to kind of look like each other. Almost every time, if you have something times du, we automatically just put that in front of you. Like I wouldn't even write this step. I would have written it as 1/4 times the integral of u to the 19th times du. And now we're back at the place where we get to use the anti-power rule. And we're going to get 1/4 times u to the 20th divided by 20 plus c. And then we're going to replace u with x to the 4th plus 5. This is going to be x to the 4th plus 5 to the 20th power divided by 4 times 20 is 80 plus c. All right. Do more examples. Let's just questions about this. There we go. Okay. Well, let's look at the next one, which is, oh yeah, I'm gonna make this real awful. Sorry. So let's say we want to find the integral of, I'm gonna make this, yeah, sure. Yeah. That seems terrible. Sine of x times secant to the 7th power of x dx. Oh, that seems terrible. So here's my usual words of wisdom when it comes to trigonometry. If it doesn't look like something you know, it's often a good idea to write it in terms of sine and cosine. So I'm going to rewrite this as sine of x times secant of x is the 1 over cosine of x. I'm write this as 1 over cosine to the 7th of x dx. Or it might even be a little bit nicer. I don't know. You might disagree. You might write this as sine of x divided by cosine of x to the 7th power. Okay. I want everybody to write down on their own without saying any words. Write down what you want to guess u to be equal to. And it is just a guess. It's okay to guess the wrong thing. I guess the wrong thing sometimes. It's part of the process. I'll give you 15 seconds to write down something. Okay. So if I had to choose something for you, I would pick cosine of x. And the reason I'm picking cosine of x is twofold. One, it's stuck. It's in the 7th power and it's also in the denominator. But more importantly, what's its derivative? Almost negative sign. But again, I don't really care about the negative, right? It's something times sine of x. And I exactly have a something times sine of x up there. So that's feeling really good to me. My du is negative sine of x times dx. I don't have a -1, so I'm going to multiply both sides by -1. So I'm going to say that -1 times du is equal to positive sine of x times dx. And then I can start rewriting this. You could write another step, or you could just say, I know that that part there, that's going to be -1 times du, or just negative du. And the bottom part there is going to be u to the 7th. But you can also write it out. You can say, I would rather write this as the integral of 1 over cosine of x to the 7th times sine of x dx, and then say more affirmatively that this sine of x times dx is -1 times du, and the cosine of x there is my u. So then I can rewrite this, I can translate this to the language of u and get the -1 I'm going to put out in front times the integral of 1 over u to the 7th du. Then to integrate 1 over u to the 7th, I need to rewrite it. So that I have u to a power, not 1 over u to a power. So we're going to rewrite this as negative the integral of u to the -7th du. And now we're going to anti-differentiate that. Okay, negative u to the -6 divided by -6 plus c. I'm going to rewrite this as positive 1/6 times u to the -6. Let's see. And then I'm going to rewrite this as 1/6 times, my u is cosine, so cosine of x to the -6. Let's see. And you could leave it like that, or you could write it as 1/6 cosine to the 6th x plus c, or you could even write it as 1/6 times secant to the 6th of x plus c. All these are totally valid ways of writing this answer. I don't think it really matters which way you write it. If I had to choose, I'd probably pick the last one. Okay. Yeah, question.
When you integrate something and have like the integrand like whatever and then like dx, do you need to write parentheses and then dx?
No, you don't. Sometimes people do, but you do not need to. It is always assumed that everything inside here, the dx is multiplied by that. So for example, if I was writing something like the integral of x to the third plus 5x squared plus e to the x minus cosine of x dx, there is absolutely no need to write that along parentheses. But it's also not wrong to if you wanted to. So it's totally fine to if you want to, but there is no need to. And just to, since I've written the question, we might as well find the antiderivative here. It's going to be x to the 4th over 4 plus 5x cubed over 3 plus e to the x plus, sorry, not plus, minus sine of x. Let's see. All right. Let's see. I think you all get to try one now. Yeah, that's a good idea. I think you all should try the following. So, yeah, I want you to try finding the antiderivative of x to the 5th times cosine of x to the 6th plus 9. Make a good choice for you. Most of it. Back in here, you start rewriting that integral in terms of u. Another minute, and then we'll talk about it. If you've got an answer and you want to check to see if it's right, take the derivative of it, see what you get. Okay, so for this problem here, integral of x to the fifth times cosine of x to the 6 plus 9 dx. The seemingly right choice is x to the 6 plus 9, and it is because its derivative is in my integral, or close enough. The derivative of x to the 6 plus 9 is 6x to the fifth. And then we're going to fix it. We're going to say du equals 6x to the fifth times dx. And then we're going to multiply both sides by 1/6 to get 1/6 du equal to x to the fifth dx, which I have in my integral. So when I'm doing this and writing less, sometimes I'm going to be like, okay, yeah, this part here, that, and that, there's my du. My 1/6 du, apologies, sorry. And down here, there's my cosine of u. So then I could rewrite this as the integral, well, I should say 1/6 times the integral of cosine of u du. The antiderivative of cosine of u? Yep, positive sine of u. So I get 1/6 sine of u plus c, and then finally, I finish the indefinite integral by replacing u with what it's equal to, and they get 1/6 sine of x to the 6 plus 9 plus c. Almost dead. And you could take the derivative here, right? If you wanted to, you go back and check. Up here, the derivative of 1/6 sine of x to the 6 plus 9 is going to be 1/6 times cosine of my stuff times the derivative of my inside stuff. And oh yeah, that's exactly going to be x to the fifth times cosine of x to the 6 plus 9. So in case you hadn't noticed already, when we're doing a u sub, we're really just undoing the chain. And if you take the derivative back again, you're going to have to end up using the chain when you do it. Yeah, we should do really, so u substitution is kind of, unless you can simplify it, make it just things you know how to anti-differentiate, u substitution is your go-to method of integration. You are hoping that your problem is a u substitution instead of something else that is honestly more terrible. U substitution is the nice thing. Everyone hopes for a u sub. And then if you try a u sub and it doesn't work, then we try other things. But u sub is what I'm always looking to hope that my integral ends up being doable by. Let's do some more examples. Let's try some things that are not too bad. Like, sure, sorry, I've ordered more pens, but they haven't come yet. The antiderivative of the natural log of x over x. What's a good choice for you here? Well, there's not a lot of choices. What are my options? ln of x is the right choice, but I'm going to explore the wrong choice for just a second. Because I want you all to see that for a u substitution, substitution has too many t's in it. Substitution, okay. U equal to x is never the right choice. Now, I want to clarify something. Later on, when we talk about integration by parts, it is totally fine and correct to sometimes let u equal x. and dv be some other stuff, which we will talk about when we get there. So I just want to make it a blanket statement that is, this is only true if we're talking about trying a u sum. And here's why. If we let u equal x, the derivative is just 1. So du is equal to dx. And if I rewrite this integral, well, here's what I'm going to get. I'm going to get the integral of, well, dx becomes du. X is equal to u. And the natural log of x is the natural log of u. And all I've really accomplished is rewriting the same exact integral with a different letter, which hasn't gotten me anywhere. So when you're doing a u substitution, letting u equal x is never helpful. You're just rewriting it with a different letter. So instead, we make the right choice. We let u equal the natural log of x. And again, it's the right choice really for just one reason here. Its derivative is 1 over x. And so du is equal to 1 over x dx. And I exactly have a 1 over x times dx. So I can rewrite the integral of the natural log of x divided by x dx as the integral of the natural log of x times 1 over x dx. And then the usual process, 1 over x times dx, that's going to be my du. Natural log of x, that's going to be my u. And the antiderivative of u to the first is u to the 1 plus 1 divided by 1 plus 1. Let's see. And then we change it back. Natural log of x quantity squared over 2 plus c. And if we took the derivative, we would get 2 times natural log of x to the first divided by 2. And then we multiply by the derivative of the natural log of x, which is 1 over x. And we definitely get back to the natural log of x over x. Let's look at some more exciting u substitutions. Yeah, let's do that. So let's look at something like, we should do some definite ones too. The integral of x squared e to the x cubed plus 4. And really, I want to look at this one so I can show you a slightly different way of approaching this. I'm still going to make what I think is the typical choice for u here. I'm going to let u equal what? Exactly. The stuff that's stuck somewhere. And also the stuff that if I took its derivative, du dx is 3x squared. So du is 3x squared dx. Okay, here's a slightly different way of approaching this. Instead of doing what I like to do, which is multiplying both sides of this by 1/3, another people sometimes do this instead, and your teacher might do this instead. They say, well, I would really love it if I had 3 times x squared in my integral. Great, I'm going to make that happen. I'm going to multiply by a 3 on the inside and a 1/3 on the outside. And 1/3 times 3 is just 1. So I haven't changed anything. I'm still going to have a 3x squared times e to the x cubed plus 4 dx. This is not my preferred way of doing it, but it's completely valid. Totally works. So then doing this, look what I've got. I'm going to rewrite this a little bit. I'm going to write it as 1/3, and I'm going to move things around and write it as e to the x cubed plus 4 times 3x squared dx. 3x squared dx is my du. E to the x cubed plus 4 is my e to the u. So I can rewrite this as 1/3 the integral of e to the u du. E to the u always feels weird because when you integrate it, you don't change it. So the antiderivative of e to the u is itself just e to the u plus c. So I get 1/3 e to the u plus c, and then I plug back in that u is equal to x cubed plus 4, and I get 1/3 e to the x cubed plus 4. C. So that's a different way of doing it. It's really not that different, but it is a little bit different. I will point out that if we had instead done the usual thing, we still would have gotten the same answer. So if I had decided to say, oh, I'm just going to do this the regular way, what I like, and say that instead of saying du equals 3x squared dx, I'm going to multiply both sides by 1/3 and get 1/3 times du equal to x squared times dx, and then take my integral and write it as e to the x cubed plus 4 times x squared dx. And then, oh, okay, now my x squared dx gets to be 1/3 du. My e to the x cubed plus 4 is still e to the u, and I still end up with exactly the same integral. It's still going to be 1/3 times the integral of e to the u du, which is still going to be exactly that, which is exactly that. So either way you do this, you're going to get to the same place. Some people just prefer to do it one way or the other. And then there's a third way, which I really don't like, but we can talk about that too. It's not that I don't, it's not actually I really don't like it. It's that there are some instances where doing it this other third way, which we haven't talked about, makes it really harder to see what's actually going on and can be kind of counterproductive to actually completing the problem. So that's why I don't like doing it this last way, which I'll show you. Let's do a few more. I know it's just examples and examples and examples, I know. But it's good to see examples. Oh yeah, let's look at that one's kind of cool. I want one more like that though. Yeah, let's do that. Sure. Let's say, yeah, oh yeah, this is a prime example of what I'm talking about. Yeah, let's do this one. Let's say we want to do, yeah, that's good. Okay. So we have the integral of e to the 2x over 1 plus e to the 2x dx. So here, I would probably make the choice of letting u equal the entire denominator. And my du, actually, let's define du, the derivative du dx. Well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. No, I guess that works out just fine. I'm just thinking. So I'm going to do this the way I like to do it, and then I'll do it another way just so you can see another way. It's different than what we just did before. So I'm going to say that du equals e to the 2x times 2 times dx. We have an e to the 2x times dx, so I need to get rid of that 2. So I'm just going to divide both sides by 2. I say that, but what do you know? I mean, I'm really dividing both sides by 2, but I actually write it as multiplied by 1/2. We know this is the same thing, but it's good to make sure we know. So 1/2 du equals e to the 2x times dx. So then I'm going to rewrite my integral as the integral of 1 over 1 plus e to the 2x times e to the 2x dx. And then we change it to u's. E to the 2x dx is equal to 1/2 du. And then 1 over 1 plus e to the 2x is going to be, all that's going to be 1 over u. So we're going to end up getting the integral of 1 over u times, watch for a second, times 1/2 du. I'm just going to put that 1/2 out in front because I can every time. So whatever constant is multiplying your du, put it in front. All right, and then we anti-differentiate, and the antiderivative of 1 over u is the natural log of the absolute value of u plus c. And then we rewrite it as 1/2 natural log of the absolute value of 1 plus e to the 2x plus c. And even though this is correct, if you look at the solutions in the textbook, it'll probably be written as 1/2 natural log of parentheses 1 plus e to the 2x plus c. Because 1 plus e to the 2x is already positive all the time, so you don't need to take the absolute value, or the absolute value of it is just itself. So we often don't write that, and often you will see it in textbook solutions that they will not write those.
I'm just, why does the derivative control those? I just forget why.
So, well, I actually want to kind of, so it's not just the natural log of the bottom. I mean, yes, it is in this case,
Yeah.
but that's not a generally true formula. For example, if I said, what's the antiderivative of 1 over x cubed? The answer for sure is not going to be the natural log of x cubed.
Yeah.
Right, we'd have to rewrite this as the integral of x to the -3rd dx,
Yeah.
and that's going to be x to the -2 over -2. Yeah. So the reason, I mean, I'm gonna say something kind of I guess, pedantic maybe. The reason that the antiderivative of this thing is because the derivative of the other thing is 1 over x. So really, reason that the antiderivative of 1 over x dx is equal to the natural log of x is because the derivative of the natural log of x is equal to 1 over x. Right? There's no other story there really. And technically we need an absolute value here in plus c. But more generally, right, the reason that the antiderivative of, say, 3x squared over 1 plus x cubed is equal to the natural log of the absolute value of 1 plus x cubed is because I did a u substitution in my head, but really it's plus c is because the derivative of the natural log of this stuff is exactly 1 over the stuff times the derivative of the stuff. So if I were to do a u sub here, my u would exactly be 1 plus x cubed, and my du would exactly be 3x squared dx. And I would be taking the antiderivative of du over u, which is the same as 1 over u du, which is the natural log of the absolute value. So that's why that happens. And then even more broadly, I will just say that it's actually true if you have your variable plus or minus a constant. So the antiderivative of like 1 over x plus 7 is going to be the natural log of the absolute value of x plus 7. Let's see. Think about the derivative. What's the derivative of the natural log of x plus 7? It's 1 over my stuff times the derivative of my stuff, but the derivative of x plus 7 is 1. Back to the problem we were looking at. So I just want to point out another way that people sometimes deal with this du stuff is some people like to solve for dx completely, meaning they take my du equal to e to the 2x times 2 dx and completely divide by everything that isn't dx. So they rewrite this as du over e to the 2x times 2 equal to dx. And this is great when it works, but there are some problems where it doesn't work and you still want to use the u substitution. What do I mean by works? Well, if I start rewriting my integral of e to the 2x over 1 plus e to the 2x dx, I'm going to rewrite that as e to the 2x times dx, which is du over e to the 2x times 2, and that's over 1 plus e to the 2x. And then the first thing I should do, if I've done it this way, is make sure that whatever is beneath the du cancels out. And then replace the rest of the things with u. So then this is going to be 1/2 integral of 1 over u du. And then we still get the same result. It just looks a little bit different in the process. I don't like doing it that way, but some teachers teach it that way. So if your teacher is teaching it that way, you should see it that way. But it works fine. Sometimes it doesn't. The other thing I want to point out here, and this problem is a really good opportunity to see that it's really, really vital that you make sure that in this problem, you deal with the dx and whatever it needs to soak up, turning into du first. Because if I had gone at this kind of just attacked it without paying attention, I might have accidentally written this as the integral of, well, no, that's not a good example, James. I'm stretching this a little here. U is minus 1 is e to the 2x. So I could have said e to the 2x is u minus 1 over u, but then I'm still stuck with this dx over here. And that's, oh, sorry, thank you. Sorry, this e to the 2x, if I subtract 1, u minus 1 is e to the 2x. And so I could say, oh, I have u minus 1 over u. And some people make the mistake of not paying attention to dx. If there's a dx still there, we can't just anti-differentiate, even though everything else has u's in it. So don't do this. It's really, really important to make sure that this gets taken care of, turning into du before we deal with any of the rest of the integrand. And I think my next example is actually a better example. What time is it? It's 4:08. Okay, so that's about 22 minutes. So much time. Okay. It feels like so much time right now. In 10 minutes, and we're like, oh my God, there's still so many things to say. Let's look at one more example of this. Yeah, I like this one. We want to find the integral of, let's say we have e to the x over 1 plus e to the 2x. Deceivingly similar. And I do mean deceivingly. Because even though this looks almost exactly like the problem we just did, the choice for our u sub here is extremely, well, it's going to feel extremely different. So I'm not going to pick u equal to 1 plus e to the 2x. Because if I did that, actually I am going to pick it first because I want to show you that you can pick the wrong u first. It's going to happen a lot. You should get used to it. Feel good about it. It's okay to make this, you're just part of the process of finding the right u is finding some wrong ones first. So my du dx, if I made this choice, would still be 2e to the 2x. And then I'm looking over here and saying, like, I don't have an e to the 2x in the numerator, which is where that would need to live if I was going to find du equal to 2e to the 2x times dx, right? I don't have e to the 2x times dx. And I really, really need to. You're out. So we're going to make a different choice. And so here is where we're going to fall back on the criteria that we really, really want to be true, is that whatever your choice of u is, we would also love for its derivative to be in the integrand. So I'm going to make the choice of letting u equal e to the x because the derivative of u is e to the x. And if I isolate du, I have e to the x times dx, and my integral has an e to the x times dx. It's right there. So sometimes we just pick u based on the fact that the derivative of our choice is showing up. Ooh, there's another good example of that too, which is kind of weird, but we'll talk about that later. Yeah, well, yeah, it's a good problem. Sorry, I'm like, oh, that's a good problem. Maybe we'll do it today. We'll see. So I'm going to start rewriting. Well, I'm going to start writing this. So this is going to equal the integral of 1 over, I'm going to save that for a second. I'm going to have my e to the x dx over here, which is just going to be equal to my du. And then I want to write the denominator in a way that allows me to see what u is. It always sounds like I'm using bad grammar, but right, we're not. We're trying to find what u is equal to. So I'm going to rewrite e to the 2x as e to the x squared. And my e to the x is my u. And then when we rewrite this in terms of u, look what we've got. We've got 1 over 1 plus u squared times du. And now we have to remember what function has a derivative that is equal to 1 over 1 plus u squared. It's close to tangent.
Oh, cotangent.
Not cotangent. It's not the reciprocal of tangent. It's the inverse tangent, the inverse function, or arctangent, as I would like to prefer to call it. So this is going to equal the arctangent of u plus c, or if you prefer, the inverse tangent of u plus c. And then we're going to plug back in that u is equal to e to the x. So our final answer is going to be the arctangent of e to the x plus c. Yeah. Right. I mean, I wouldn't call this a rule other than that if you know the derivative of a thing is the function you're looking to antidifferentiate, then you know the antiderivative. So really, this is just, we know this antiderivative because of a rule of differentiation. Just like if I asked you to find the antiderivative of cosecant of x times cotangent of x, we know the antiderivative here is negative cosecant of x, because we know that the derivative of cosecant is negative cosecant times cotangent. So, right, no rule other than just that's how it works. Yeah, there's one I want to do, but it's interesting to me, not because it's important. Let's go ahead and yeah, we should do that. So we should talk about some definite integrals for a moment because we haven't really. So let's look at, where'd you go here? Yeah, let's do this one. Start out with something not too terrible. The integral from 1 to 9 of x minus 1 over the square root of x. Yes. So whether you're doing a definite integral or an indefinite integral, the methods of integration are still applicable, meaning if you can just simplify it, you should. So here, I'm going to rewrite this as the integral from 1 to 9 of x divided by x to the 1/2 minus 1 divided by x to the 1/2. You can also make the alternative choice of writing this as the integral from 1 to 9 of x minus 1 times x to the negative 1. Either way you do it, you should input the same thing. We're going to get the integral from 1 to 9. X to the first divided by x to the 1/2 is x to the 1/2. And 1 divided by x to the 1/2 is x to the negative 1/2. Or if you prefer, x to the first times x to the negative 1/2 is x to the 1/2. And 1 times x to the negative 1/2 is x to the negative 1/2. Either way gets you to the same spot. And now we're going to use the anti-power rule. So we should get used to doing this fast. When you anti-differentiate something and the power is a fraction, you're going to get that fraction added, right? Just like every time, you're going to add 1. And then instead of dividing by that fraction, we're going to automatically multiply by the reciprocal. So the antiderivative of x to the 1/2 is x to the 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. Divided by 3/2 is the same as multiplying by 2/3. Minus x to the negative 1/2 plus 1 is x to the positive 1/2. Divided by 1/2 is the same as multiplying by 2. I don't require a plus c because it's a definite. You could write one if you wanted to, but it's really, really unnecessary because they end up canceling each other out when you plug in and subtract. Then we plug in, we get 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2 minus, you plug in 1. Okay, 1 to any power is 1. So we're going to get 2/3 times 1 minus 2 times 1. And then we should simplify this because we can. 9 to the 3/2 is the square root of 9, which is 3 cubed, which is 27. So we have 2/3 times 27 minus 2 times the square root of 9 is 3 minus 2/3 plus 2. And then 2/3 times 27 is 2 times 9, which is 18 minus 6 minus 2/3 plus 2. We've got 12 plus 2 is 14 minus 2/3. And then that's 42/3 minus 2/3, which is 40/3. If I were doing this problem on an exam, I would stop here. If I had time, come back and simplify it further. But I would do everything else first before doing any more arithmetic to find out what this looks like nicer. Okay. Yeah, we got time. Okay. But really what I want to address is, what if you have a definite integral that requires a u substitution, like the integral from 0 to 4 of x divided by the square root of 9 plus x squared? Well, let's see what happens. So let's make our choice for u. I'll let you all take a second to write down what you think you should be. I see only one plausible choice for you. Technically, you could say there's two plausible choices. So the two technically plausible choices are the right choice, 9 plus x squared, and the less good choice, the square root of 9 plus x squared. But if you have the choice between a thing and a more complicated version of that thing, pick the less complicated version first. And if it doesn't work out, then try the more complicated version. So then my du is going to be 2x times dx. So 1/2 du is going to equal x dx. So then I'm going to rewrite this integral. I'm going to write it, I'm going to actually write it the same. I'm just going to change up a little bit. I'm going to write it as the integral from 0 to 4 of 1 over the square root of 9 plus x squared times x dx. My x dx is 1/2 du, and the 9 plus x squared is my u. Okay, so here's an important thing that's going to happen. When I rewrite this, I'm going to choose to change my limits of integration. Let's write the integrand first. I'm going to get 1 over the square root of u. And I would normally pull out the 1/2, but I'm going to leave it in here for a moment just so that we don't have to think about all the things at once. So there's my new integrand in terms of u instead of in terms of x. But I will point out my limits of integration, those were x values. This is from x equals 0 to x equals 4. And now my integral is in terms of u. And there are a couple ways to do this, but I think the best way to do this, and most people agree, the best way to do this is usually to change your limits of integration. So I'm going to change my x values to whatever the corresponding u value should be. So u equals 9 plus x squared. If x equals 0, u is going to equal 9 plus 0 squared, which is 9. And if, right over here, x equals 4, u is going to equal 9 plus 4 squared, which is 16 plus 9, which is 25. And what's great about doing it this way is after you've done the antiderivative, you do not just do not, you should not, you cannot, it is wrong to plug back in what u is equal to in terms of x. You get to leave it in terms of u and then just plug in your u values. So doing it this way, here's what we're going to get. We're going to get the integral from 9 to 25 of 1/2 times u to the negative 1/2. We're going to antidifferentiate. We're going to get 1/2 times the antiderivative of u to the negative 1/2 is u to the positive 1/2 divided by 1/2, which is multiplying by 2, evaluated from 9 to 25. And then I'm just going to write that as the square root of u evaluated from 9 to 25. Because the 2 and the 1/2 cancel. And then I just get the square root of 25 minus the square root of 9, which is 5 minus 3, which is 2. And that is how I would recommend doing a problem like this. But not everybody likes to do things the same way. So let me just point out, if you did this a different way, let me show you how you would do that. But let's say from right here, we decided not to change the limits of integration. So instead, we said, we're going to rewrite the integral from x equals 0 to x equals 4 of 1 over the square root of 9 plus x squared times x dx. We're still doing the u sub and writing it as 1 over root u times 1/2 du, but we're not changing limits of integration. So I would, preferably, I would write them in as x equal to 0 to x equal to 4. The one thing you shouldn't do here is write just 0 to 4. If you write 0 to 4, someone's going to think that you don't understand that the limits of integration should have changed, and you're saying u equals 0 and u. Or you can not write any limits of integration, but I don't prefer doing it that way. I think that's wrong, personally. So then we're going to do the same thing. We're going to rewrite this as 1/2 the integral from x equals 0 to x equals 4. 1 over the square root of u is the same as u to the negative 1/2. We antidifferentiate. We get 1/2 times u to the 1/2 divided by 1/2 is the same as multiplying by 2. From x equals 0 to x equals 4. The 2 and the 1/2 cancel. We get the square root of u from x equals 0 to x equals 4. We plug back in that u is equal to 9 plus x squared. And then we go from x equals 0 to x equals 4. And now we can plug in the x values and get the square root of 9 plus 4 squared minus the square root of 9 plus 0 squared, which still ends up being the square root of 25 minus the square root of 9, which is 5 minus 3, which is 2. This to me is the less good way to do it. It's a fine way to do it if you want to do it that way, but I think you're saving yourself a little bit of writing and effort if you decide to change the limits of integration to the corresponding u values, and then you don't have to change back to x's. You just have to leave it as u's. I like that better, and most people tend to like that better. Okay. Let's see here. Yeah. Let's do one more. Let's do the following. Yeah, that'll be good. Let's say we want to find the definite integral from, yeah, let's say 0 to, well, let's do that. Pi squared over 9. Yeah, that'll be good. Of cosine of the square root of x divided by the square root of x dx. Yeah, I like that.
Sorry, I was in a class here earlier.
Uh-huh.
I left behind this small green notebook, feeling quite too
I didn't see anything up here when I got here. Anyone see a small green notebook? Haven't seen it. You're certainly welcome to wait a few minutes and look around after we're done. Yeah.
I'm so sorry.
No, that's all right. So here, anyone see a good choice for you? Yeah, what is it? Yeah, excellent choice for you. Really, in my opinion, the only plausible choice for you. It's both in the denominator and in the cosine function. It seems like a really good candidate for you. But now I'm worried about this derivative actually showing up. Well, oh, let's find out. So if u is x squared of x, let's write that as x to the 1/2. My du dx is going to be 1/2 x to the negative 1/2. Bless you. I would not love to leave this way because it makes it harder for me to see what I want to see. I would encourage you all to get used to taking the derivative of the square root of x and immediately rewriting it as 1 over 2 square root of x. Right? X to the negative 1/2 is the same as 1 over x to the 1/2, which is the same as 1 over the square root of x. So the derivative of the square root of x is 1 over 2 root x every time. And then I'm going to rewrite this as du equal to 1 over 2 root x times dx. And oh, I'm feeling pretty good about that because I see a 1 over root x times dx. I just need to get rid of that too. I can say that 2 times du is equal to 1 over root x times dx. So then I can re-express this. Again, you don't have to do this intermediate step. I just find it so much more convenient to write this with the piece that I want to turn into du kind of separated out. So I would really recommend writing this as cosine of the square root of x times 1 over the square root of x times dx. I like doing that. Do not have to do that. That's my 2 times du, and there is my leftover u. Right. So again, this is an important example of making sure that your du soaks up whatever it needs to before we start replacing things. Because if we weren't careful, we might have written this as cosine of u over u, which we shouldn't. It's cosine of u, and then the other root x down there needs to go up into the dx thing to get to turn into du. All right, let's rewrite this thing. It's going to be the integral of, we're going to change the limits of integration in a second. These are x limits of integration. We're going to change them to u limits of integration. I've got cosine of u times 2 du. I'm just putting that 2 out in front, like I always am going to do with a multiple of du. And then if u is equal to the square root of x, well, x equals 0 means u is the square root of 0, which is 0. And if x equals pi squared over 9, u is going to equal the square root of pi squared over 9, which is the square root of pi squared over the square root of 9, pi over 3. And I'm done with x's. We don't have to change back. Great. I feel like you make an ex partner joke there. I'm done with my x. I'm sticking with you. It kind of works, kind of. Okay, so then we anti-differentiate. We get 2 times sine of u from 0 to pi over 3. And then we plug in and we get 2 sine of pi over 3 minus 2 sine of 0. The expectation here is that we do evaluate these. These are values that we are capable of finding the values of. I should say they're angles we're capable of finding the sine values of. Sine of pi over 3 is root 3 over 2. Sine of 0 is 0. So this simplifies to just the square root of 3. All right. It's 4:29. I think that's close enough to 4:30 that we should call it a day.